Hello and good evening, everyone. My name is Bhavedeep Rai. Welcome to week 7 problem solving session for the course theory of computation. This week's topic is bijections and undecidability. Okay, and as always, before moving on to the main part, okay, we'll be solving few of the questions from the previous assignment. This is from uh, assignment 6. Okay. I'll leave out the simpler ones for you and we'll discuss only the tougher ones. So I've picked these two questions, questions 12 and 13 from the assignment 6. Okay, so let me begin with the discussion. So the question says the following: recall the definitions of PTAs. Okay, now what are PTAs? PTAs are just PDAs with queues instead of stacks. And multi-stack PDA from week 4. So I think you guys remember, but I'll just repeat. PTA is again what? This is just a PDA. See, normally what does PDA have? PDA has a stack, right? But with queue instead of a stack. What is stack? Well, stack is also what is called the first in, last out. So the idea is that you can just keep, I just keep what is called the push operation. I can keep pushing and then I pop. Or instead of saying first in last out, I can even say last in first out. I think that is how it is generally called. The last to be pushed is the first to be popped. Okay, and whereas what is a queue? A queue is like a queue of people, right? So the first person to go in is the first person to come out. So the pushing happens at the end, right? And the popping happens at the back. So queue is an example of a first in first out system data structure. First to go in is the first to come out. Now, what are PDAs? PDAs are like DFAs, right? You go from one state to another. It is just another computational machine. But the machine has a special memory which is of the form of a stack. And whereas PTAs, we are saying instead of a stack, we have a queue instead. Everything else remains the same. There are number states and some kind of tape alphabet where you can push it on the queue and so on. Everything remains the same, only that it is a stack instead of a queue. And we proved some results in the previous assignments regarding PTA. This was what is called the push-through automata. Push-through automata. Anyway, what does the question say? If a K-stack PDA can emulate any Turing machine, what does emulate mean? It can behave identically. It can behave like a Turing machine. Okay. Then the minimum value of K is something. In other words, question says, if I rephrase the question, it says, how many, okay, also a multi-stack PDA, okay, before I move on, multi-stack PDA is just a PDA with several stacks, 2 stacks or 3 stacks or something like that. Okay. So the question says, how many stacks are needed to simulate a Turing machine? Emulate a Turing machine is the correct word actually. Now, what does a Turing machine has? A Turing machine again has state, it has several symbols, and so on. But the main thing that distinguishes it from, PDA or something like a PTA, okay, or a finite state machine is the fact that it has an infinitely long tape. So it has a tape, and you can write wherever you want. A, 0, B, and so on. And you have a head, right? And this head can move right or left, and then it can make changes as you go along. My claim is, okay, so the question is, if I am allowed to have several stacks, if the PDA is allowed to have several stacks, how many stacks are needed to sort of simulate this motion, sort of behave like a Turing machine, do everything that a Turing machine can do? My claim is that 2 stacks are enough. My claim is that 2 stacks are enough. Why? Let the 2 stacks be A and B. Okay, so let's see. Let the 2 stacks be A and B. So this is what the stack looks like. There's another stack. Okay, and let's say there's a bottom symbol dollar. Okay, now this dollar tells that the stack is empty. Okay, now at any point, okay, A represents tape contents of the Turing machine, okay, at the left side of the head position, and including head, current symbol. Okay, and same thing at any point, stack B. What does stack B do? Stack B represents the tape content of the Turing machine at the left side of the head. What does it mean? Example, let's say this is the tape content. This is the tape. Okay. Now, let's say the head is pointing here and the symbol is 0, 1, 1, 0, 1, 0, 1. Okay. And let's say, since we know that an infinitely long Turing machine on both sides can be written as a Turing machine with infinitely long tape only on one side. Let's say this part is, okay, the end, left end marker, or let's just keep it like this. Okay, then what does the corresponding stacks on the PDA look like? The 2 stacks, it will have this 0, 1, 1, okay, and along with the head, along with the current position is 0. Next it has 1, 0, 1, 1, let's say 1, 1, 0, 1. Okay, and this is the current position. Okay, this part is this part, and I choose a color green. This part is this part. Okay, is sorry, this part. So I hope you can already see where this is going. Now, if in the Turing machine head moves right, then instead of pointing here, I should point here, no, which means this symbol should be on top of the stack, right? I should be pointing here, so this symbol should be on top of the stack, and now 0, okay, this will no more be there, and therefore 0 will be to the right, so 0 should be here, shifted there, right? So if head moves right, okay, then pop symbol from stack A, push it to stack B. Pop symbol from stack A, push it to stack B. So this 0 will be pushed here. So now the top of the stack A represents the current symbol. Okay. Top of stack A is the current symbol. So we can now already tell what happens if the head is supposed to move left. Right. So if I move, sorry, not this is for left. So sorry. Head moves left, then so if head moves right, then this guy is supposed to be the right. This guy is supposed to be the top of the stack of A. So from B I will pop and push it onto A. If in the Turing machine, right, head moves left, if the head moves left, then what are you supposed to do? Pop symbol from stack B and push it to stack A, because that is the new head position, right? And if current, and what is Turing machine also capable of doing? Wherever it is pointing, it is able to change that particular element also, right? If current symbol is changed from say A to B, right, where AB, okay, no, it's changed from say some symbol A and to some symbol in B. A, B are in tape alphabet. Or in other words, in terms of Turing machines, in terms of transition function, it will be like delta of the current symbol, no, current state, Qi A is equal to some Qj. A will be changed to B, and then either move left or right. Right, either left or right. If such a thing is happening, then what if that is this 0 here that we are pointing at is changed to 1, what are we supposed to do? We are supposed to pop from A and push that new symbol onto A. Then pop top symbol from A, right, that is this current symbol is A, is popped off, and push B to stack B. That is good. So all of a Turing machine's behavior is captured by PDAs with 2 stacks. So anything that a Turing machine can be done can be done by a PDA with 2 stacks. So answer is 2. So we see that just by increasing the stack by 1, it makes the machine so much more powerful. Additionally, by the Church-Turing thesis, right? I mean, it is said that Turing machine is the most powerful machine that you can have, right? Anything an algorithm can do, a Turing machine can do. So just by adding 2 stacks, you are able to do so much more. Okay. So let's go to the next one. If a KQ PTA can emulate any Turing machine, then a minimum value of K is. So now we have asking what is this question, in other words, says what is the number of Qs? What is the number of Qs to emulate a Turing machine? This is the question. The answer is just 1. Why can we answer it so easily? Because 2 stacks can be simulated by a single Q. Okay. You can use a single Q to simulate 2 stacks. Well, using a single Q, how would you simulate just 1 stack? Okay, I think we've done it before once. So we were imagining the stack to look like this: A, B, C, D. Okay, and the Q would store something like this: D, C, B, A. Okay, so D, C, B, A, and if you pop here, you can pop here, and if you want to push something, first you need to push something, then you need to keep popping things at the back and push it in at the back. So first you need to take C, B, A, okay, and say D is popped off. Okay, once. So if you want to push, you can take D, C, B, A. Okay. Okay, and you have C, B, A there, no? C, oh, okay, yeah, of here, of course. You put a C, to push, you first put a D, okay, to push, first push, not D, let's say I need to push a E, push E, pop D. Okay, I popped D. First I push E. Okay, now what will my Q look like? I can only push it at the back. So C, B, A, then E. Next, keep popping. So what do I do? until E is reached. So if I keep popping until E is reached, so I'll get E, C, B, E. Okay. So this is how I can simulate this. If I simply need to simulate two stacks, then I can use a single queue by using a demarcation symbol. Let's say a dollar sign, and this part represents the first stack, and this represents the second stack. So this is one way to do it. Another way to do it is, of course, like you can imagine the queue. Okay, imagine the tape of the Turing machine. Okay, and then you have the queue here, right? What you can always do is you can consider the front of the queue, since we only know what is front of the queue and the back of the queue. You can consider the front of the queue to always represent current symbol. You can always use the front symbol, the front of the queue, to always represent the current symbol. So if this is the current symbol, here you have it, and then everything to the left of it, okay, everything to the right of it can be, let's say this is everything to the right. And then what you can do is you can add a demarcation symbol, let's call it dollar, and after dollar whatever will come will represent the left of the queue. So now I'm not going to do it in detail because it's similar to what I've done previously, but the idea is that if the head needs to move left, okay, or simpler, let's say first I'll do, if the head needs to move right, then what will I do? I'll simply pop this from the front and push it at the back, because that is how a queue works, right? You pop from the front and you're only allowed to push at the back. I'll push it at the back. Then what is the new head? This is the new head. Now what if the queue moves left? Sorry, what if this head moves left? Then I need to keep popping, okay, and I need to get here, right? So yeah, I need to keep popping and pushing until I reach here. So first I pop this, I put it here. I pop this, I put it here. I pop this, I put it here, and I keep doing this until my front of the queue is this. And you can work it out yourself. You'll see that this dollar still maintains the fact that to the left of the dollar I'll have all the elements to the right of the marker, and this to the right of the dollar I'll have all the elements which are left to the marker. Okay, so you can verify that yourself, but I'm not going that in too much detail. Okay, so this is another way to show. So the answer is 1. Just one queue is enough to represent, or in other words, one queue is enough to represent the infinite tape of a Turing machine. Okay, so yeah, those were some interesting questions based on the assignments. Yeah, now we'll move on to the topic of this week. Okay, undecidability. So here we'll talk about a few things. First, I'll just do a small recap. Okay, now say so what is a decidable language? A decidable language is a language that has a Turing machine which always halts and gives correct answer. Okay, a Turing machine that solves the language will always halt and give the correct answer. Now, what is an undecidable language? Undecidable language is the complement of decidable is a decidable complement. So that is Turing machine does not always halt. Okay, and so let's make a Venn diagram for it. This is a bit too small. So you have the set of all languages, also shown by power set of sigma star. Why? Because any language is a subset of sigma star. So the set of all languages is the set of all subsets of sigma star, right? So what is the set of all subsets of sigma star? It's power set of sigma star. So you have decidables here, which is shown by D. Okay, and everything outside D is undecidable. Okay. Now the question what we want to explore is, at least in the first few lectures, is this area outside decidables. What does it look like? Well, it turns out that there are, levels of difficulty even for undecidable languages. So undecidable languages means very difficult problems because you don't have Turing machine for it. But even they have different levels of difficulty. The first one is Turing recognizable. So that means, in other words, the Turing machine recognizes the language. Okay, what is meant by Turing recognizable language? Turing machine, there is a Turing machine for the language that always halts in the yes case. So a Turing machine in a decision problem that says yes or no, okay, testing for this language at least, it is always whether something is in there in the language or not. So if the string to be tested is there in the language, it will always say yes. The machine will always halt and say yes. But if it so happens that the string is not in the language, then it may not always halt, it may loop also. May not always halt in the no case. Right. For example, I think there was a problem that said about polynomial, talked about polynomials. So question is, does a polynomial have integer roots always or not? Okay, it may not have integer roots, but polynomial, okay, the question is, given polynomial, does it have integer roots? Well, I can Well, if it does have integer roots, what I do? Okay, so for example, x square plus 2x minus 1 equals 0. This is the polynomial I have. So is this in the language? The language is, what is the language? L is P such that P is a polynomial with integer roots. This is an equivalent way to formulate it. Now, the question we ask is, given a polynomial, does it have integer roots? So, can we build a Turing machine to decide it? Well, if I have a following Turing machine, okay, and input is called P, let's say, okay. So I go over, 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and so on. Go over each of them and check, go over, let's say, x equals, and check if p of y, p of x is equal to 0 or not. If yes, then that particular value is a root. So say yes and halt. This is what my Turing machine will do. Otherwise, what it'll do? It'll just keep looking for it. No. So it'll just keep looking for it, and it will never end. If, let's say, the polynomial did not have integer roots, we are just looking over all possible integers. No. So this is an example. But what if? So it will never find it. But take into account the fact that if the integer existed, we will always sooner or later encounter it, and then make the polynomial evaluate to 0, and then say yes and what. So that means that if the given polynomial definitely has integer roots, the Turing machine will always say yes and halt. But in the no case, it is not halting. So it is a Turing recognizable language. So this means L is Turing recognizable. Now, another fact is any decidable language is Turing recognizable, right? Any decidable language is Turing recognizable, because a Turing recognizable means it calls in both the cases, yes and no. Okay, but Turing recognizable means that it may not halt in the no case, but even if it halts in the no case, it's not a problem. It's still Turing recognizable as long as it halts in the yes case. So therefore, all decidable languages are Turing recognizable. Okay, so this part, Turing. Okay. Now, yeah, the remaining part, this week is focused on the study of such languages. Okay. Yeah, let's begin. Question says the following. Let A and B be two finite sets such that size of A is equal to size of B is equal to n. What is the number of bijective functions possible between A and B? So here they are saying there are two sets, A, both are finite, and B, so that size of A is equal to n, both the sizes are equal. Question is, what is the number of bijective functions possible between A and B? What is a bijective function, first of all? Bijective function is both 1, 1 and 1, 2. Right? Both 1, 1 and 1, 2. So what is meant by 1, 1? For Okay, let's do on to first. Okay, for all for all. So let's say f is the function. For all b, okay, p and b, and f inverse of b is there in A. So for any element I take in B, I will always find a corresponding some value of A always maps to that. Okay. And what is onto? Oops. For all elements A in or it's rather defined as follows. If there are two elements, okay, they must be if there are two elements then in B that are mapped from F, they must be mapped to from distinct elements. It cannot be something like this is not possible. Something like this is not possible. Oh, sorry. Sorry. Yeah, this is not possible. This should always be possible. But take care that these kind of elements may exist that don't get mapped to at all. But dwelling on to these kind of elements cannot exist. There should be some kind of element that is getting mapped to that. Okay. So, like I said, something like this is not allowed. So if for all A1, A2 in A, if f of A is equal to f of A1 is equal to f of A2, then it must be that A1 was equal to A2. It cannot be that they are separate. Yeah, it cannot be that there are two separate elements in A that are mapping to the same element in B. Okay. Now, what does a bijection look like? Now, what does a bijection look like? Bijection is both 1-1 and 1-2. Because it is 1-1, because it is 1-1, one element gets mapped to one element, element gets what to one element, and so on. Something like this cannot occur. Because it is onto, it should be mapped by some element, and it cannot be mapped by this guy because it is a function. It is contradicting the meaning of a function. So it can only be that there is an element here. So this is what a bijection will look like. Every element on B side is covered by the function, and every element in B side is covered by distinct elements in A. This is what a bijection looks like. Why is a bijection important? Bijection, okay, showing bijection between two sets shows that their sizes or their cardinalities are same. Getting it? If there is a set A, there is a set B, and there is some kind of if I can show a bijection, then it means that their sizes are same. Okay. Now, so this is a very common tool in discrete maths, in mathematics in general. Okay. So this is they say how many number of bijection possible between A and B. So this is a simple combinatorial question. So if I have A and I have B and I take this And okay, so now I want to count. Okay, I have element 1, I have element 2, 3, and so on. I'll just number them randomly. So a can 1 can be mapped to some element in B, or, and I'll call this A1, A2, A3, AN. So I'll call this B1, B2, B3, B4, and so on till Bn, since both are same size. Then A can map to B1, or A can go to B2, or A can go to B3, A can go to B4, and so on till Bn. So it is number of bijections, okay, number of bijective functions is nothing but the number of choices for f of a1 plus number of choices for f of a2 plus and so on till f of an. So how many choices for f of a1? There are n elements here, so there are n choices. How many choices for a2? Now let's say a chose something. Let's say a chose this guy. How many remaining are there? There are n minus 1 remaining. So how many choices for a2? A must choose from the remaining n minus 1. Now similarly, how many for a3? It must choose from the remaining n minus 2 and so on. Sorry, this is not plus, this is multiply, because it is an AND case, right? A has n many choices and B makes n minus 1 many choices. A2 makes n minus 1 many choices, and so on. And so on until there's only one choice remaining, and this is nothing but n factorial. So what is the answer? C, n factorial. Okay. Okay. Another question based on countability now. Which of the following options are true? Okay. Sigma star is countable, but power set of sigma star is not. Sigma star is uncountable, but power set of sigma star is not. Sigma star and power set of sigma star both are countable. Sigma star and power set of sigma star are both uncountable. Firstly, sigmas, anything that is countable, okay, can be listed. All elements can be listed in some particular order, such that every element in the set appears in the list. Okay. Any countable set can be listed so that every element in the set appears in the list. Sigma star is countable. Why? Because I can list it. It can be listed in what order? In lexicographic order. How? Well, first I do a 0, then I do a 1, then I do a 0 0, then I do a 0 1, then I do a 1 0, then I do a 1 1, then I do a 0 0 0, 0 0 1, and so on. Can be listed out in this order. And this is the normal lexicographic order. The rule is just alphabet. The next person in the element is always lesser, okay, in comparison to the previous person. So lexicographic order. And every string is guaranteed to appear here, every binary string. So this is nothing but sigma star. So this is countable. Now the question is saying either A is true or B is true, right? Sigma star is countable, but parset is not, and sigma star is and parset both are countable. So now the question is the parset countable? The answer is no. A power set of an infinite set is never countable, even if that particular set used to be countable. Why? Because of Cantor's. In the lectures, we saw Cantor's argument. Cantor's argument, Cantor's theorem, let's call it, shows there does not exist a bijection between set A, an infinite size set A, and power set of A. If you want to recall how he did it, or if you want to recall the proof for the real numbers and natural numbers, real numbers versus natural numbers, we listed out all the real numbers and then found a diagonal string. We took the diagonal and then flipped it each, showed that it does not exist. We can do a very similar thing for the power set also, right? So what we do is we take what is called the characteristic string, okay? So although this is not really required, but any and A, let's say B is a subset of A, then what I can do is this characteristic represented by chi. B is a string which consists of string B1, B2 and so on, where Bi equals 1 if and only if the ith element is in A. Okay, and this I'll leave as an exercise to you guys, but show that the diagonalization shows that if I take different choices of B, okay, and B can be taken as 0, 0, 0, 1, 1, 0, 1 and so on, and this is another choice of B, 0, 1, 0, 1 and so on. Take care that this is infinite, because A is an infinite set. The subset length, the string length is also infinite, and show that the diagonalization would imply that our bijection is not possible. But what is this? If I take all of these strings, what is this? This is nothing but the power set of A, right? I mean, they are represented as strings, but as sets, they are still the power set of. As sets, together if we collect them, all of them, then they are just subsets of A. So together we collect them, they form the power set of A. Okay. So yeah, here is a question on decidability. Which of the following statements are correct? there is a decidable language L that is not Turing recognizable. There is an undecidable language L such that L is both Turing recognizable and co-Turing recognizable. All decidable languages are Turing recognizable. All decidable languages are co-Turing recognizable. These are the questions. Okay. Now let's recall this. Co-Turing recognizable. Oh, sorry. Turing recognizable and decidable. So the first option, okay, and this is this part is undecidable. Okay, everything outside decidable is undecidable. So they are saying there is a decidable language L that is not Turing recognizable. But Turing decidable D is inside Turing recognizable, right? So it cannot be the case. So A cannot be true. Next, it's saying, okay, I will come to B. Let's look at C. All decidable languages are Turing recognizable. All decidable languages are Turing recognizable, and that is evident from this Venn diagram. Any decidable language is inside Turing recognizable. So C is true. Now, before we look at B and D, we'll look at what is called co-Turing recognizable. Okay. Co-Turing recognizable languages are those languages such that their complement is Turing recognizable. That's the name. You may have seen it in the lectures. Also in the lectures, okay, I'm not going to tell why. In the lectures, it said that Turing recognizable intersection co-Turing recognizable is exactly what the decidables. So in fact, the picture looks more vivid. It's not just that D is contained inside Turing recognizable, but including the fact that D is an intersection of Turing recognizable and co-Turing recognizable. Okay. Now it says there is an undecidable language L. Undecidable meaning outside decidable, which means everything here is undecidable. Undecidable language L such that L is both Turing recognizable and co-Turing recognizable. That cannot happen. B is false. Why? If there is an undecidable language L that is both Turing recognizable and co-Turing recognizable, then it should lie here, right? It is both Turing recognizable and co-Turing recognizable. But this is exactly the set of decidables. So B is false. Finally, all decidable languages are co-Turing recognizable. All decidable languages are co-Turing recognizable. That is true. Okay. So the correct options are C and D. All decidable languages are Turing recognizable, and all decidable languages are co-Turing recognizable. Okay. Now consider the following language. No act is defined as follows. It is the set of, okay, this is the description of Turing machine. Okay. This means description of a Turing machine called M. Okay. Description of a Turing machine M such that M does not accept the string 101010. Is the problem Turing recognizable or not? So let's see. If I need to build a Turing machine for this, how do I know whether M does not accept 101010? Well, the direct question would be I'll just run M. Okay, my universal Turing machine will just run M on the input 101010. Let's do this. Run M on 101010. If it accepts, then what should I say? Say no. If it accepts, then what should I say? It should say no. And if it rejects, say yes. All well and good. But what if M does not halt on 1010? What if M does not halt at all on 101010? But this is a problem, right? Because then on running M on 101010, I'll just keep waiting for it to accept or reject. But if it accepts, I'm guaranteed to say no. If it rejects, it's guaranteed to say yes. But if it loops, I just keep waiting. But remember, if it loops, it means that the language does not belong to M. Okay. If sorry, yeah, the string does not belong to the language of M. If it belongs to the language of M, it means it halts and accepts. So if it loops, it is as good as rejecting actually. But we just don't know when to stop it. So if M accepts 101010, and let me call this bigger machine description of machine Turing machine M prime. If M accepts 1010, then definitely M prime says yes. However, if M does not accept, that is, it may reject or loop. If that happens, M prime says no or loops. M says, sorry, because we are talking about the case when it does not accept, right? It accepts, then we should be saying no. If it does not accept, then M prime says yes or loops. What is this? One way is it is directly the definition of co-Turing recognizable. Okay. Next, another way to show this, okay, that it is co-Turing recognizable is, or alternate approach. Okay, what is the alternate approach? The alternate approach is look at the complement of the language. NoAC is all the descriptions of M such that M does not accept 101010. So NoAC complement is a set of all strings, all the machines, such that M accepts 101010. And this is Turing recognizable. Why? Because again, what is the machine for it? I'll just run M on 101010. If it says yes, if it accepts, then I'll say yes. If it does not accept, then it may loop. Okay, so in the yes case, it will definitely weaken. In yes, in case we know if it accepts 1010, we definitely know. We would definitely know by just running it. No case may loop. What does this mean? This means NoAC is Turing recognizable if NoAC complement is Turing recognizable. Its complement, remember the complement of a Turing recognizable language is co-Turing recognizable. So its complement is co-Turing recognizable. And I will not so at this moment we only know whether this particular language NoAC is either recognizable or co-Turing recognizable, but it may lie somewhere in between, right here, which is exactly decidable. May lie somewhere in between, but currently I'm not doing. But in the next session, I'll show that it cannot be inside decidables. It needs to be here in co-Turing recognizable. So right now the answer is quite vague, but in the next session we'll see why it is here, because it meets the idea of reductions, and there is an interesting reduction. Yeah. Hello, Krish, am I audible? I'm audible, right? Oh, okay, thanks. Okay, so so here's the question. Okay, so the question says, is the following language decidable or not? The question is called, the language is called same DFA. Okay, what is the inputs? They are two DFAs. Okay, D1 and D2, and they are in the language only if language of the first DFA is equal to the language of the second DFA. Okay, so input, there are two DFAs, D1 and D2, and the output is yes if L of D1 is equal to L of D2, and no otherwise. If they have different languages, then they will say no. Question is this language decidable? Is this problem decidable? So this is another way to state it, right? Is this problem decidable? In other words, can we find a total Turing machine for it? In other words, can we find a Turing machine that will always halt, that will correctly say yes and no, yes or no, and that will correctly say yes or no, and it will say yes only if the languages are identical. Okay, so how do we solve this problem? So here we'll use the closure property of regular languages or closure properties of DFS. Recall that regular languages are closed under union, intersection, and complement. They're closed under union, intersection, and complement. Now we'll do an interesting thing. We'll look at what is called the XOR or symmetric difference. Okay, what is the symmetric difference? Asymmetric difference B, okay, also called parity. Okay, asymmetric difference B is the set of all it is the set of all strings, all the elements X, such that X is in A as well as X is in B. So, in other words, here is a Venn diagram: A, B, and this part, this part is A, sorry, oh, what am I saying? Okay, it is the opposite of that. Okay, A is not in B and X is in A is not X is in A, X is not in B, or X is in B, X is not in A. So what is the symmetric difference? They are these part, exactly the opposite of intersection. Since it is exactly the opposite of intersection, I hope you can already see that it can also be written as follows. And by the way, A XOR B can be written as follows. Okay. A complement intersection B union A intersection B complement. You can verify this later. You can try this as an exercise. Okay. This is exactly B complement union intersection A. This is exactly A complement intersection B. Okay. And then this is the union. So this we can easily compute. We can always build a DFA computing A XOR B, asymmetric difference B. Okay. Because why? Why? Because it consists of intersections, unions, and complements. Nothing is violated here. By violated, I mean, see, if I do a complement, I can find a DFA for this, and this is also regular, so I can find a DFA for this. This is also regular, and the union is also regular. So the entire thing is regular. You can always make a DFA for this, and it's constructive. You can use some kind of subset constructions to achieve this. Getting it? So we can always build a DFA which computes a symmetric difference B. Now, what do we observe? If A is equal to B, then imagine these two circles, fusing in. Okay. A is equal to B. There is no element that is in A and not in B, and there is no element that is in B which is not in A. Okay. So if A is equal to B, this is A, and the same thing is B also. So there is no element which is outside, inside A but outside B, and inside B but outside A, as you can see. Then, or you can also think of this as follows: A complement B union A intersection B complement, right? So um, yeah, so A complement intersection B is nothing but B complement intersection B union B complement intersection B complement, which is empty set union empty set, which is empty. So if A is equal to B, it is empty. If A is not equal to B, similarly you can say that this is A XOR B is not empty. Now the question is, now here's the algorithm. Here is the algorithm, okay, or the Turing machine description. Okay, the input is D1 and D2. What do? Construct DFA D1 XOR 2. Let me call it D XOR computing L of D1 XOR L of D2. Okay. Now all I need to check whether it is empty. Check if the language computed by D of XOR is empty or is fine. If it is empty, then what would it imply? They are the same set. Output yes. If no, output no. Now, it is not over yet. Why is step 2 possible? How to check if language of this is empty? Simply check if there is a string that lands to the final state or not, or simply check that is it even possible to ever land in the final state. If final state is not reachable, if final states are not reachable, then no string will be accepted, right? If no string will be accepted, then the language is empty. Language of that particular DF is empty. If the final states are not reachable at all, then language is empty. Okay. And how do you do this? You can simply use some DFS or BFS. Okay. Next, we'll look at another question called enumerator machine. Okay, based on enumerator machine. So enumerator machines. Okay, what is an enumerator machine? So consider a machine called the enumerator machine, defined as follows. An enumerator machine E consists of a single tape where it can write symbols from an alphabet. Okay, gamma union some hash. Okay, during its run, it writes strings on the tape separated by this hash. It may print the strings in any order, even repeat strings. Okay, so here is a machine E, and E can write strings and so on. The language of the enumerator machine E is the set of strings printed on E's tape during its execution. So what is the language? It is the set of all strings that are printed here, not counting the hash. Okay. And I'll and furthermore, if a string X is in E's language, then it is guaranteed to be printed on the tape during E's execution. Okay. So, hello. Akshay, am I audible?
Yes, sir.
Yeah. Okay. Yeah. Today's session is a bit short, so this is the final question. Actually, I'll just discuss this one question. Okay. We'll
Okay, sir.
from the beginning, and we'll wrap up after that.
Okay, sir.
Okay. So yeah, I'll repeat the question. So consider a machine called the enumerator machine. Okay. And it is defined as follows. An enumerator machine consists of a single tape where we can write symbols. Well, it can write symbols from an alphabet, gamma union hash. Okay. And during its run, it writes strings on the tape separated by hash. Okay. And it may print the strings in any order and even repeat strings. So here is an example of an enumerator machine. It's called E. Okay, and like a Turing machine, it has a tape and head and so on. But the tape is read only. Okay, and it prints strings during its run. It will print string as follows: 1011 and hash, then 011 and hash and 101 and so on. Okay, the language of the enumerator machine E is a set of strings printed on E's tape during its execution. So whatever the strings are printed, okay, besides the hash, is together they form the language of the enumerator machine. Now, furthermore, if a string X is in E's language, then it is guaranteed to be printed on the tape during E's execution. If it is in the language, then it will get printed. It may take a long time, but within a finite amount of time, it will definitely print it. Okay. Now, it says, for example, say an enumerator E prints on the tape epsilon 1010 and this 101010 and notice that it is printing it in any order. It could print it in any order. It may not be increasing order or something like that. And also that it may repeat strings. For example, this is repeated. So repetition is also possible. But what is the language is all the set all the strings that are printed here is the language of the enumerator machine. Now the question says the following: which of the following statements are true about enumerator machines? Okay. Okay. Firstly, any enumerable language, which means any language of an enumerator machine, okay, is a Turing recognizable language. And the second says any Turing recognizable language can be enumerated by an enumerator, which means any Turing machine recognizable language is an enumerable language. So it means that both of them are the same. Okay. If A and B both are true, then it means the two languages are same. So therefore, the models of enumerator machines and Turing machines are also equivalent. Let's see. Let's see A. Any enumerable language is a Turing recognizable language. So let's say L is a enumerable language. What does it mean? L is an enumerable language. There exists a enumerator machine such that language of that enumerator is L. Okay. Now we want to test if it is Turing recognizable also. Okay. Now what is Turing recognizable? Language is Turing recognizable if we can construct a Turing machine such that when the Turing machine is set to say yes, the Turing machine always halts. Okay, that is, if the string is in the language, then the Turing machine always halts and says and accepts. If the string is not in the language, then the Turing machine may loop. Okay, so here is a Turing machine. Okay, Turing machine M on input, let's say X. Okay, the idea is very simple. We will just simply run the enumerator machine and it will start printing on the tape. Okay, run E and use M's tape as E's tape. So what does E do? From the definition, it starts printing these symbols which are there in E's language. Okay, and if E prints, let's say if prints a Y, a string Y on the tape, okay, let's say this is Y, okay, on the tape, such that Y is equal to X, the input given to us, then accept. Then it means that that particular X was in Y's language also, was in E's language also, and that's it. This is the description of the Turing machine. Now let's see why it is okay. So if X is in the language L, then X is in the language of L of E. If it is in the language of the enumerator, then what happens? Then E is guaranteed to what was written. If a string X is in E's language, then it is guaranteed to be printed during E's execution. Okay, then E is guaranteed to print X on tape. Now if it is guaranteed to print X on tape, then Y such that Y equals X is always printed. Such a Y is always found because X is in the language, X will definitely print it. But if let's say X is not in the language, if X is not in the language, then what happens? E will never print a Y such that Y is equal to X. E will never print a Y such that Y is equal to X, and this means M will never halt. But even though M will never halt, it is fine because we just want M to be Turing recognizable machine, right? Yeah, I mean the language of M to be Turing recognizable. No? And we can see that Y okay is in the yes case, that is if X is in L, then yes case it prints yes and halts always. So during the yes case it always halts, which means that the language of the machine is Turing recognizable. And what is the language of the machine? It only accepts those strings which are printed by the enumerator, so which is nothing but the language of E. So both are same, and therefore language of the enumerator is Turing recognizable. Okay, so this is sort of the easier direction. So we'll look at the second direction. Any Turing recognizable language can be enumerated by an enumerator. Any Turing recognizable language can be enumerated by an enumerator. So this time we'll do the opposite. We'll take a Turing recognizable language. Let L be Turing recognizable. Okay. And since it is Turing recognizable, there is a Turing machine for it via a Turing machine M. Right. The Turing machine may not always halt. Now we want to create an enumerator, which means we want to have a mechanism of writing on the tape and starting enumerate, behaving like an enumerator basically, printing all the strings in the language. So here is a simple way to, here is the first attempt, okay? Here is the first attempt. First attempt is as follows. Description of enumerator E. Okay. Now, enumerator does not have any inputs. If you recall, it just keeps blindly printing symbols on the tape. So first what I'll do is I will go across all y, or I'll call it x. X equals, everything. X in sigma star. Go across all x in sigma star. For each of these x, check if M accepts x. Okay. And 3 is if M accepts x, then write hash on tape followed by x. For example, like if say 101 is accepted by the Turing machine, then on the tape we'll write 101 and then hash. Okay, sorry. Hash and then 101. And let's say the next we try on 110 and it is not accepted, then we won't write on the tape. And let's say 111 is accepted by this this Turing machine, right, by M, then we'll write 11. So since the language of the enumerator is not nothing but the strings that are printed on the tape, right, since it is nothing but the strings that are printed on the tape, the language of the machine M is identical to the language of the enumerator that we constructed. But there is a slight problem with this, small problem. Can you think about this for a while? What may be the problem here? The logic is straightforward. We are trying to build an enumerator, and we go across all possible strings, and we check whether the string is accepted by M or not. If it is accepted, then we write the string on the tape, and we keep doing this, and we've built an enumerator, right, whose language is same as the language of the machine M. So this looks like it is sufficient, right? Do you think there's any problem with this? The key is in the fact that M is a machine for a Turing recognizable language. Okay. Uh, Here's the problem. Problem is that since M is since the language L, okay, is Turing recognizable, we haven't said that L is decidable. So the Turing machine corresponding to it may not be always halting, right? It may not always halt. So if I do this check if M accepts X, when I run it on X, I may go across some bad inputs where it may never halt. And as soon as that is encountered, my enumerator machine will never print anything after that because it will keep looping in step 2. It'll keep looping in step 2. Okay. So the problem is M may not halt in some inputs because L of M is only Turing recognizable. We didn't say they are decidable. So now this seems like a huge problem, right? Because now we cannot build an enumerator. But there is a simple thing that we can do. We can do parallelization. We can run on all inputs in parallel. We cannot run on all inputs in parallel. That is one thing. But we can run as follows. Okay. So this is one trick to do it. And that is, let's say these are the inputs X. That look like epsilon 0 1 0 0 0 1 0 0 0 0 0 1 0 1 0 0 1 1 and so on. First what I'll do is I'll run on epsilon for one step, then I'll run for 2 steps, okay, and this for 2 steps. Then I'll run on epsilon for 1 step and for 3 steps, and then 0 for 3 steps and 1 for 3 steps, and so on. Or I can even do 1 step each. Why 2? So first step, step 2, step 3, and so on. I can run 1 step each and then 0 for 1 step. I basically continue the computation. Okay. So we recall some of the computation. We recall on the tape whatever computation we've done. And so this is similar to something you would do in operating systems. Okay. In operating systems, you have this problem of parallelizing processes. No? So what do? You just run one process for a while. Okay, one clock cycle, what we call a few clock cycles, and then the next clock cycle you run the second process, and then you keep doing this, and that is giving you the illusion of parallelization. Internally, the operating system is not doing parallelization unless you have multiple cores. If you have a single core, then it is achieving parallelization using this. Similar, you're doing a similar thing. So this is what is also called time sharing. So what do? You do check M accepts X in a time sharing fashion. Now, if you do this time sharing process, this time sharing circus, then what happens is that even if, let's say, on an input 1, it was supposed to loop, I bypass this and then move to the next input. Okay, fine. In 1, it does not, it keeps looping. It's okay. I'll move on to the next strings and I'll try for other strings. And if it so happens that, for other strings, it suddenly says yes, then I'll just output that particular string, let's say 0, 0 for this case. And then the process will just continue without worrying whether for certain inputs my machine will halt or not. And yeah, so then we've built an enumerator. So what does that mean? What is the key takeaway? any enumerable language is Turing recognizable, and any Turing recognizable language is enumerable. That's why sometimes you may even hear that it is called a recursively enumerable language. Turing recognizable languages are also called recursively enumerable languages. And because of this property that they can be enumerated in this fashion. Okay. And okay, with that, we've come to the end of the session. So is there anything that you would like to ask? If any additional thing you'd like to ask, then otherwise we can wrap up this session.
No, sir.
Okay. Okay, then the next session will happen on Tuesday 6 p.m. same slot. Okay. Okay, then. Thank you. Good night, Akshay.
Thank you, sir. Good night.
Okay. Bye.
Bye, sir.